Yeah, thank you, Kristina, for introducing me and also for giving me the opportunity to present Professor Alejandro Franco. So I'm going to start sharing my presentation that basically I was asked to set the scene of today's presentation and give a glimpse on the Battery 2030 Plus roadmap, especially on the manufacturability chapter. So basically, we have different challenges in manufacturability, and looking from the near term to long term, I have included certain names there in which we are currently facing, but we identify also in the long term that will need to be addressed. So one is the sustainability, for sure, ensuring sustainability and ensuring reducing environmental aspects should be covered with all the manufacturability work. Efficiency, we need to address to improve efficiency in terms of resources, but also in cost. Also accelerate the scaling up processes in different materials, and also deal with the standardization, providing guidelines and protocols to standardize the manufacturing. In the long term, within the Battery 2030 Plus initiative, we have a new adventures, new challenges coming from, because we foresee we will have new chemistries, but also we will need to address new manufacturing routes. Also, there will be new functionalities like the self-healing properties of materials and components, or even sensors to put in place in the cells, and all these need to be covered and addressed within this long vision that is covered in the Battery 2030 Plus. But I don't want to forget on the recyclability aspects, because it's somehow closing all the circle in the battery field. So all of this is covered within, as I said, in the Battery 2030 Plus roadmap, and also in particular to the manufacturability. Dealing with the manufacturability in the roadmap, we have addressed these activities from the Industry 4.0 perspective. So what we aim to have digital tools covering not only the manufacturing, but also the cell performance. So if we start from the current lithium-ion manufacturing routes, like the current roll-to-roll, we should have very accurate models, models that mimic the processing, but also machine performance in a way that we can control perfectly how machine parameters are impacting on the outcome on the components like electrodes, cells, or certain steps like electrolyte filling. So within the roadmap, we visualize these accurate models that mimic the manufacturing, but also that need to be efficient in computationally talking. Also, this is related to the manufacturing, but we cannot forget on the digital twin of cells, in which we mimic all the scales of the cells, and even we are capable to reproduce virtually the degradation of cells. So this is in the roadmap seen is in a coupled vision, coupling cells together with the manufacturing, that in the end, we are able to perform inverse design so that we can, for certain application, we can know exactly which are the best components and how need to be manufactured. So this is somehow accelerating this, these digital twins will accelerate the scaling up, will make the manufacturing more efficient and for sure more sustainable. And this is seen from the very holistic view. So as I said, we are dealing with digital twins capable to mimic these cells from the multi-scale approach that can be multi-physics based models, but also data-driven models or even surrogate models in order to have this efficient codes that can reproduce cell behavior in a number of cycles, but coupling and also addressing all the scales all along the cell. So these digital twins of the cells will be coupled to digital twin of manufacturing, but also we need to address the flexibility or the modularity of the manufacturing, because currently we are working on the roll-to-roll application in which we manufacture electrodes but different steps like slurry preparation, drying, coating, or calendering. But in the near term or longer term, there might be different manufacturing routes like the additive manufacturing, 3D printing, extrusion, or whatever that need to be available for different chemistry that will come out in the soon. So also in the battery 2030 plus, it's seen as an holistic view. So we're dealing with the standards, providing guidelines, recommendation, and a standard language in order to monitor all the manufacturing steps. So this is obviously seen as an holistic view, but we cannot forget that within the battery 2030 plus, we have set up different approaches like the big map or even self-healing and sensors implementation. So manufacturing is somehow closing all these aspects that are already covered within the battery 2030 plus and need to be, we also include them as a way to accelerate the scalability of these approaches. So with this, I would like to end my presentation and present Professor Alejandro Franco, that he will be presenting the talk, and he will be presenting digitalization of the battery manufacturing processes, why and how talk. Professor Alejandro Franco is a member of the Institut Universitaire de France and leader of the, Theory Open Platform at the ALISTORE European Research Institute. He holds an ERC Consolidator grant for his project artistic on the digitalization of battery manufacturing processes based on multi-scale modeling and artificial intelligence. He recently won an ERC Proof of Concepts grant for his project Smart Artistic of the assistance of the battery manufacturers using mixed reality. He is the chairman of the expert group Digitalization, Measurement Methods and Quality in the Lee Planet Battery Manufacturing Network, and he won the French Prize for Pedagogy Innovation 2019 for his use of virtual reality to teach battery sciences. So yeah, now I leave the floor to Alejandro Franco and to his presentation. Thank you.
Thank you very much, Elixabete, for the kind introduction. And I will share my screen.
Yes.
Do you see my screen? Do you see my screen?
Yes, sorry. Yes,
perfect.
We can see.
Great. Thank you. Thank you very much, Elixabete, once again for the kind introduction. And I also would like to acknowledge Kristina for the kind invitation. So I feel very honored to be here today in this great series of seminars organized in the context of Battery 2030 Plus. And well, as Kristina and Elixabete mentioned, so I'm going to talk about digitalization of battery manufacturing processes, why and how, right? That's the title of my seminar today. And first of all, I would like to say a few words about my laboratory, the laboratory I'm coming from. So I'm coming from the Laboratory of Reactivity and Chemistry of Solids in Amiens, which is a city located in the north of France. So we are part of two networks, the RS2E, which is the French network on energy storage, and ALISTORE, which is the European Research Institute, dealing mostly with battery technologies. And in our laboratory, we are about 130 people with more than 20 nationalities represented, working mostly in the battery field, right? And we are also very much interested on the battery manufacturing and batteries prototyping based on both lithium-ion and sodium-ion technologies. And in this regard, so we have in our laboratory a prototyping unit. We have also created a startup a few years ago to devoted actually to sodium-ion batteries, and the name of this startup is Tiamat. As we are very much interested on the topic of battery manufacturing, so we are also very interested on the topic of digitalization of battery manufacturing. And in this regard, so as Elixabete mentioned, so I'm holding a ERC project called Artistic, in which we intend to develop a digital twin of the battery manufacturing process with a particular focus on lithium-ion batteries based on both physics-based modeling and machine learning models. And so several examples that I'm going to show today to illustrate how we can digitalize the battery manufacturing processes are taken from this ongoing project. Okay. For the followers of this project, so you will see that I will share some old examples, but also I will share several new examples of some of our very recent publications published this year or even yesterday. Okay. Okay, so then the first question is manufacturing digitalization. So why we should try to digitalize the manufacturing process, right, of lithium-ion batteries in particular? Well, as you know, lithium-ion batteries, they are everywhere, right? They are even allowing the re-emergence of electric vehicles. And inside the cells of these lithium-ion batteries, so we have electrodes, right? And depending on the spatial location of the active material, the conductive additive, mostly carbon particles, and binder, so this cell is going to have different cells energy densities, different power densities, different lifetime, and safety. Therefore, it's very important to control the interfaces between these materials inside the electrodes. And in order to control the interfaces between these materials, of course, we need to talk about how we manufacture these electrodes, right? The manufacturing process of lithium-ion battery electrodes is highly complex. It involves multiple steps and multiple parameters. First of all, so what we do is we mix materials in a solvent, right? So we mix the active material, the carbon additive, the binder in a solvent. We mix them. We prepare the so-called slurry. Then, so we cast the slurry on a current collector to prepare the first electrode of this lithium-ion battery cell. We pass the resulting coating in an oven, okay, in order to evaporate the solvent, and then we get the dry electrode, right? Then, so what we perform is the calendering, which consists of applying a pressure, okay, on top of the electrode in order to improve the electronic contact between the particles. And then, so we will perform the same thing for the second electrode. We will put a separator in the middle, and we will perform the winding, right, in case that we are interested on, cylindrical cells. The step after this one is, of course, the electrolyte filling, right? We need to fill the cell with a liquid electrolyte in order to ensure the proper exchange of lithium ions between the two electrodes. And then, so we are going to close the cell, right? And then we will get this lithium-ion battery cell ready to use, right? So as you saw in the slide, so manufacturing a lithium-ion battery electrode is like cooking, right? So you really need to choose the right parameters in the right way in order to make proper batteries, right? Proper battery cells. Indeed, so when you take a look on the number of parameters involved here along this manufacturing process, so what we can say is that this is a very complex parameter space because we have multiple parameters, but also a lot of interdependencies between these parameters. You can actually represent the lithium-ion battery manufacturing process as a different gears which are linked with each other in a sequential way. And if you remove or you tune not in a proper way one of these gears, then so the final result, which is a lithium-ion battery cell, will not be what you desire, right? This is why it's very important, first of all, to understand the links between these different process steps and the impact of these links between the different process steps and the involved parameters on the resulting lithium-ion battery electrode microstructure and also lithium-ion battery cell performance. State of the art for doing this, trial and error, right? And of course, if we are doing trial and error, so we should expect high scrap rates, right? If you are, for example, at the prototyping level, so we could estimate that you will have scrap rates of around 30%. While if you are manufacturing cells in a series with a very well-established protocols and so on, maybe you will be around 5%, right? But still, this is a lot, right? And something that battery manufacturers are dreaming is having somehow a digital twin, which is actually a copy in the computer of the actual manufacturing process, which can provide through actuators real-time indications to the machine on how to optimize the manufacturing process of the lithium-ion battery electrodes, right? If in order to have this concept working, in order to have this digital twin that can provide real-time instructions to the machine, of course, we need also to implement in the machine sensors. Then the topic of sensing is also very important towards the development of a digital twin, because these sensors are going to collect real-time data in the machines and they're going to fill this digital copy in order to feed it, and then in a way that this digital twin can provide recommendations to the machines, right? But what we have in the core of this digital twin, so how this is possible, how we can imagine copies in the computer that can provide real-time recommendations to the machine in a way that the machines can by themselves optimize the different manufacturing steps involved in this process. Well, this is possible because in the core of a digital twin, so what we have are models, right, or computational models. And actually, so we imagine two types of models in the core of this digital twin. So physical models, which are actually models based on the description of the physics going on between the different particles, which are being mixed, which are being cast, which are being dry, and so on and so forth. These kind of models, they can be very useful for understanding in more detail, so the different manufacturing steps and the influence of the different manufacturing parameters on the electrode properties, but also they can be very useful for predicting, right, the influence of manufacturing parameters on electrode properties and cell performance. In the other hand, so we can have machine learning models. These machine learning models are very, very useful tools to discover correlation between input parameters and output parameters. And this is very important, in particular, when you are dealing with a highly dimensional parameter space. So we are dealing with many parameters, right? And this is typically the case in lithium-ion battery manufacturing. And then, so these models, they can also very, very useful to derive surrogate models, simplify versions of the physics-based models that can be integrated in optimization loops. That means in algorithms that can perform quasi-real-time optimization, right? So these type of models, they have both cons and pros, right? So first of all, so if we talk about the physical models, if you go to a three-dimensional description of the battery manufacturing process, you can get very high accuracies, okay? You can have in that way high fidelity models that are going to describe the process almost as it is in reality, right? However, with this kind of models, you will have a lot of computational cost because you need to solve complex differential equations in 3 dimensions. In the other hand, so if you use empirical models, so you will have a very low predictability, okay, because you need to fit a lot of parameters, right, with experiments. But of course, as this takes the form maybe of an algebraic equation, so these kind of models, they will have very, very low computational cost. In the other hand, so a machine learning model so needs a lot of time for training. In particular, if we are talking about supervised machine learning techniques, then here you have a high computational cost. But while these models once these models are trained, so then they can have very high predictability, so they can make very good predictions, with very high accuracy, with very little computational cost. You can basically predict, so very high accuracy in a question of seconds, right? So you see then that these two techniques are highly complementary, right? In the vision of developing a digital twin. And this is why, so in the artistic project, we are dealing with both, right? So we are dealing with modeling the manufacturing process based on physical models and modeling so the manufacturing process based on machine learning models. In the next 50 minutes, okay, I'm going now to show you examples, okay, of different models that we are developing in this project for each step of the manufacturing process, starting with the electrode slurry, right? The electrode slurry, as I mentioned at the beginning, so it's a suspension of active material, carbon additive, binder, so in a solvent, right? In order to model that, so based on physical modeling approach, so we use a coarse grain representation of the particles which are in the suspension. And we define basically two types of particles for no aqueous slurries, which are representative, for example, of slurries containing NMC 111 as an active material. And here the two types of particles that we use is the active material particle, which is the grain representing an active material particle, a secondary particle of NMC 111. And we define a second grain, which is the CBD particle, which is carbon. CBD stands for carbon binding domain. And this particle contains carbon, binder, and solvent. We do in this way because if you start to describe all the atoms and molecules present in this system, so you will need a very huge computational cost in order to solve the system of equations that will allow you to predict the slurry structure, right? That's why we simplify the system with this coarse graining approach. And instead of representing the interaction between atoms or molecules, we will represent interaction between these effective particles of grain, active material, and CBD. So thanks to this simulation, so we are going to be able to predict in 3D microstructures of slurries, right? And then so the input of this model, this coarse grain molecular dynamic simulation, so using this coarse grain representation will be the active material particle size distribution, that is something that we can extract from experiments, and of course the formulation, the weight percentage ratio between active material and CBD, right? And for an aqueous slurry, so the approach is similar, but instead of describing the interaction between two types of particles, CBD and active material, we add a third entity, which is called the solvent particle, okay? And this is something that allows to accounting very well, so the viscosity and density properties of aqueous slurries. It's something that we realize by trying different approaches, right? So the similar way to no aqueous slurry, so the input of this model is the active material particle size distribution and the weight percentage ratio between active material and CBD. The difference with the no aqueous slurry is that in this approach, the CBD particles, they don't contain solvent, right? They only contain carbon binder and some nanoporosity inside, because the solvent is described as itself as a single type of particle, right? Then how it works, this technique actually, the coarse grain molecular dynamics approach to simulate slurries. So basically you start with a box, you place randomly in the space the different type of particles that you have. For example, for a no aqueous slurry, you will have CBD particles and active material particles. Then you will solve the interaction forces between these different particles. More precisely, you will solve Newton equations with forces here acting on each type of particle resulting from Lennard-Jones force fields and granular Hertzian force fields that are going to describe attraction and repulsion between the particles. They are going also to describe the cohesion between the particles, the viscous behavior of the collection of particles, and so on and so forth. And then so by solving these Newton equations, you will reach at some point at the equilibrium state, minimal energy of the system, and you will converge to the slurry microstructure, right? Once you get this virtual slurry microstructure in the computer, so then you can characterize it in terms of the density, in terms of the viscosity, and then you can compare the numbers that you get in the computer with the ones that you can characterize at experimental level. And here you see examples for the viscosity calculated as function of the applied shear rate for two different slurry formulations and for different solid contents, right? And you see here a very good comparison of what we calculate with the model with what we can get at the experimental level, right? Here, of course, in order to have this very good fitting, so what we do is we fit the parameters, these 6 parameters which are represented here in red in the equations, in order to match perfectly all the conditions, right? In order to do so, we use optimization algorithms, okay? We use particle swarm optimization and machine learning. Just to give you a flavor of how we do this, we basically use this combination of a technique called functional principal component analysis and k-nearest networks, which is a kind of machine learning technique, in order to predict the result of this coarse grain molecular dynamics simulation before the simulation ends. In that way, so we can, as we can predict from the very early steps of the simulation, we can predict what will be the viscosity value that the simulation will be able to obtain. Then so we can integrate this as this forecasting technique in an optimization loop that allows us to fit the experimental curves more quickly, right? And this concept here that we have published very recently as a preprint, it works for slurries made of NMC 111, LFP, or graphite. Before, so we were needing few days to fit a viscosity curve with one of these models. Nowadays, we need only few hours to fit a full viscosity curve coming from experiment with this kind of model. The second step is the coating and the drying. And this is something that we simulate also using coarse grain molecular dynamics. And the way that we proceed is the following. So we take this virtual slurry, we shrink the CVD particle size, okay, in order to mimic the solvent evaporation. Then all these green particles here representing the CVD, which initially contains carbon binder and solvent, they become smaller. They become they're represented now here in yellow. Then the interaction forces between the particles change, and then we relax the system again. So we run once again molecular dynamics. So we solve Newton equations. And then so the final state of this simulation will be the dry electron microstructure. And this dry electron microstructure, you see here in red, the active material particles, and in yellow, the carbon binder domain, which in this case doesn't contain any more the solvent, right? And this virtual electron microstructure so can be validated with, for example, with different type of descriptors, such as the porosity of the virtual electrode. And this porosity of the virtual electrode can be compared with the experimental one, right? But also you can imagine calculating the electronic conductivity of this virtual electrode, the tortuosity factor, and so on and so forth, and compare also with the experimental values. The model is also able to capture the impact of the drying rate on the microstructure, and in particular on the phenomenon called as CVD migration or carbon binder migration. And here you see how this works. Basically in the model, so we imagine that the CVD will shrink at different rates depending on the depth of the slurry. So if you are in the current collector side, the CVD will shrink at a rate much slower than the one that is on the top. And then in that way, so we are able to calculate, to predict electrode structures that will be heterogeneous along the electrode thickness in terms of CVD volume fraction, right? And this is something that can be very nicely also quantified. I mean, if you track the evolution of the CVD volume fraction, so along the thickness of this slurry that then is becoming an electrode, you see that for high drying rates, you know, if you focus, for example, on this series of 3 red curves, you see that there is a high heterogeneity. You have much more CVD on top than at the bottom, right? And this is actually explained because when you apply high drying rates, so then you favor the motion of these particles, and then CVD is much more mobile and can go more to the top because of convection forces, right? Why, when you apply low drying rates, so you give time to the system to calibrate more nicely, right? And then so the structure will be more homogeneous. So we have less deviation or less gradient of CVD volume fraction along the electrode thickness, right? And this is something that is very interesting also to capture, that the model is able to capture, is that this CVD migration phenomena doesn't start from the very beginning. So you have always a kind of delay here, right? It starts sometime after that the drying process starts, right? And these two aspects, the CVD migration for high drying rates and the fact that this CVD migration doesn't start from the very beginning, these are two experimental facts, okay? This model is actually finding things that have been already observed at the experimental level. And this is something that we have discussed in this paper, which appeared last year in energy storage materials. You can also address the topic of, you know, slurries, coating and drying, so using machine learning. And this is a quite old work that we have published actually 2 years ago. But it was, as far as I know, so the first one, so addressing this problem in such a way, I mean, using machine learning. And basically here, so what we have done is we collect experimental databases. So as an input, we were playing with the slurry formulation, the solid content, the viscosity, and we were measuring the impact of these 3 parameters on the active loading of the electrode and the porosity of the electrode at fixed drying conditions, right? So then we collect this kind of data sets here that you see, they're very noisy, right? You cannot tell anything very clearly here. And then so what we had performed is an application of machine learning, a supervised machine learning technique called support vector machine, which allows transforming these noisy data sets in something that is more understandable or readable by the experimentalists, right? Basically, this support vector machine technique allows transforming this collection of this cloud of points in phase diagrams for battery manufacturing. And here you see an example of a kind of result that can be obtained with this technique. So here you see the impact of the formulation, that means the amount of NMC that you have in your slurry in weight percentage, the impact of the solid content of your slurry, and the impact of the viscosity on the slurry on the porosity that you will get in the electrode after the drying process. And here you see that this actually output is telling you that in order, for example, to make electrodes with low porosity, which in this case means electrodes with more or less 30 to 35% of porosity, you need to choose the appropriate content of an MC, right? The appropriate formulation. And also you need to choose the appropriate viscosity for your slurry and the appropriate solid content, okay? Because if you choose, for example, for this case, a viscosity which is too low and a solid content, okay, that is, okay, whatever value you want between 60 and 70, so then it will be for you impossible to make electrodes with low porosity. If you want an electrode with low porosity, so you need to increase the viscosity value and mostly use high solid contents, right? So this is the kind of outcome that this kind of machine learning modeling can give you, right? And we believe that this is very useful for experimentalists because this is a kind of phase diagram, right? It can very easily understood by the, for example, the technician, which is making battery electrodes in the pilot line, right? This concept for, you know, casting, mixing, drying, and so on, so can be also extended to other battery technologies, and in particular solid-state batteries. And this is a work that we jointly published with the group of Shirley Meng last year, where we extend this methodology that we have developed in the previous paper I showed in the previous slide to the concept of developing solid-state separators, right? And here, so we use as an input of the machine learning workflow, so the formulation, which is in this case controlled by the amount of polymer that you put in your slurry, the liquid to solid ratio, the co-solvent ratio, and so on and so forth. And then so we derive a model, which is also a supervised model, which is able to predict under which formulations and under which casting conditions you will get so separators, solid state separators with high uniformity and high conductivity, right? The next step in the digitalization of battery manufacturing is the calendering. The calendering is a very important step because you need to press the electrode in order to improve the electronic contact between the particles, right? But at the same time, you need to avoid to press too much because you will otherwise collapse the pores, and then it will be very difficult for the liquid electrolyte to go in, right? And then you will have problems with wettability of your electrodes. Therefore, it's very important to optimize this process, right? And to perform calendering, but not too much, right? And this is why some modeling also can be very useful in this regard. In order to model, so based on the physics-based approach, the calendering process, so we use a technique called discrete element method. This technique is like molecular dynamics. So you describe here the interaction between particles, but in this case, instead of describing the interactions through Lennard-Jones or granular Hertzian potentials, you will describe interactions through mechanical forces, right? More or less. So here you have as an input of this discrete element method model, so the electron microstructure predict from the drying model, okay? And remember that the input of the drying model is the slurry microstructure predict from the slurry model, right? So you see that the models are sequentially connected. So it's really a digital twin of the real manufacturing process from the slurry to the calendering, right? This discrete element method model so is able to predict the impact, for example, of pressure, okay, or degree of compression on the microstructure of the electron, right? And here, so you see an example of simulation. So this is for one applied pressure. You see that the model is able to predict how compression compress the electrode, right? The thickness decrease. Then you have a plastic behavior there. But also you see that at the end of the compression, the electrode recover a little bit the initial thickness, right? So there is a recovery effect. And this is also observed experimentally, right? That means that the model is able to capture both plastic and elastic behavior of the electrodes upon calendering, right? And you see here that the model fits very well in terms of porosity that is being calculated upon compression. So the experimental values, okay, of porosity versus applied pressure during the calendering process step. The model is fit also based on microindentation experiments, okay? And that's why the model is capable to capture both plastic and elastic behavior of the electrodes upon calendering process step, right? Once we get these electron microstructures coming from the calendering simulation, where in blue you have the active material particles and in red you have the CVD, then we use a software which is called Innov. It's a software that we have developed in MATLAB, which in-house, right? That is capable to transform these files, which are represented here. The output actually looks like a collection of spheres placed in space, right? It transforms this file in something that is readable by computer programs able to calculate, for example, tortuosity factor of your electrode, or programs able to simulate the electrochemical performance of the electrode, like, for example, constant multiphysics. Basically, more precisely, what this software does, it applies a technique called boxerization, or meshing, right? It meshes the electron microstructures in a way that can be read in computing programs that are capable to simulate electrochemical performance or calculate properties such as tortuosity factor. And you see that when you apply this boxerization technique or this meshing procedure to these electron microstructures predicting from the calendering, you get electron microstructures that don't look anymore like a collection of spheres. They look more like a real tomography image of an electron, right? Which is very nice, right? At the end of the day. Then, so what you can do with this is you can inject this in a software. In this case, we use Tau Factor, which is a software developed in Imperial College using MATLAB. And then, so we can evaluate the impact of the applied pressure on the tortuosity factor along the Z direction, which is the thickness of the electron, right? But also we can evaluate the impact of the calendering pressure on the tortuosity factor across the plane, across X and Y. So what we observe here, as expected, also from experimental point of view, is that when you increase the calendering pressure, the tortuosity factor increases. But then at some point it reaches a plateau, because then it's not possible anymore to calendar the electrode, except if you will crack the particles, right, in that situation. So this is very interesting, as you will see later on, because if you have electrodes we have actually that have been calendared a lot, you will have high tortuosity factors, and therefore for the electrolyte wettability, you will have more troubles, right? This work actually, which consists of simulating slurries, drying, and calendering, so using the physics-based model, so was extended for other type of materials. I mean, beyond NMC and beyond graphite, right? That is the materials I was talking at the very beginning of this seminar. So we extend this work for organic materials for sodium-ion batteries as a demonstrator that these artistic manufacturing models are chemistry neutral. They can apply to different types of chemistries, even chemistries that are far away from the ones that we use currently in lithium-ion batteries, which are commercial, right? Like NMC, 111, graphite, and so on. Here, so then we move from lithium-ion batteries to sodium-ion batteries, from inorganic to organic active materials. So we use we move from commercial NMC, for example, to an in-house synthesized active material, which is this NO2 BPDC here. And we move here from NMP-based slurries, what we simulate with NMC 111, for example, to water-based slurries. And also we move from high active material weight percentage, typically 95 weight percentage of NMC 111 in our simulated slurries, to a much lower one, so typically 60 weight percentage for NH2 BPDC. And what we did is we characterized experimentally the viscosity curve as function, the viscosity as function of applied shear rate. We fit the calculated viscosity with the coarse-grained molecular dynamics model, representing this collection of active material particles and CVD containing carbon additive, binder, and solvent. Then, so once we get this good fitting, so then we perform the simulation of the drying process. We shrink the CVD size, then the electrode structure forms, right? And then, so we fine-tune the parameters in order to recover the experimental porosity. You see that the simulated one is 70%, and experimental is also 70%, more or less, right? And then, so we perform calendering, okay, of this virtually generated electron microstructure, right? We compress at different degrees, right? 10% means that you compress from the initial thickness 10% of the initial thickness, 20% of the initial thickness, and so on and so forth. And then we characterize these electron microstructures, these virtual electron microstructures, in terms of their electronic conductivity and in terms of their tortuosity factor through the pore network, which is supposed to actually be wet with the liquid electrolyte to transport sodium ions, right? And then we plot this kind of graph here where you see the ratio between the calculated electronic conductivity divided by the tortuosity factor of these virtual electrodes. And you see that the model predicts that when you increase the compression degree, of course, this ratio here will start to increase because the electronic conductivity start to be better and better because you percolate more and more the particles, right? But then you reach a kind of optimum here because here you are dividing by the tortuosity factor. That means that if you compress too much, the tortuosity factor is becoming, of course, higher and higher with the compression degree, but at some point will become too high okay? And then so the penalty coming from this increase of the tortuosity factor will overcome the benefit that you will have on compressing the electrode on the electronic conductivity, right? And this is why then we observe from the modeling point of view, you keep compressing, so this ratio will decrease, right? And then the model says also, is something I'm not showing here, is that you cannot compress more, because then the simulation becomes unstable, right? So particles are moving like a crazy way, right? I mean, it's somehow we are reaching the physical limit, you know, of the model. What is interesting to see is that we found something very similar at the experimental level. I mean, when you make electrodes with different compression degrees following the same protocol that we have established in the computational side, you see that the electrode, which has a 50% of compression degree versus the initial thickness, is the one which performed the best. And also from the experimental point of view, we show that it's impossible to make electrodes with this formulation above 50% of compression. I mean, if you want to compress more, it becomes not possible. Actually, the particles start to crack and you cannot cycle the battery, right? So this, we believe, shows once again that these artistic physics-based models are chemistry neutral, because we said nice demonstration that we can move beyond, so lithium-ion batteries, beyond commercial active materials, and we can even move now to organic batteries, right? You may wonder, okay, here we are using in these models the concept of a spherical representation of active materials, right? But this is something that we have, I mean, as you could see in the previous slide, so it's not, I mean, it's a satisfactory assumption, right? Because still you can make good predictions, you can get good validation with experiments and so on with the spherical approach of active materials. Nevertheless, so we have developed an approach which is more sophisticated, but it's even more realistic in terms of representation of the system. And here, so what we did is we start from tomography images, micro CT tomography images. Then we have developed an algorithm which is able to extract the real particle morphologies from these micro CT images. And then so we perform all the simulations of the slurry, the drying, and the calendering using the real particle morphologies, okay? And then, of course, we compare the outcomes in terms of microstructure with what we get from tomography, once again, for different formulations and for different compression degrees. So we believe this is also a step forward towards this digital twin of the manufacturing process, because now we are able to take into account real particle shapes, right? And not only spheres. Even though spheres, we can get satisfactory results, right? And we can get good predictions anyway, right? You don't need to actually take home message here is that you don't have to complexify the model if it's not needed, right? But here we want to do it just for fun, right? Just because, okay, are we capable with this workflow to simulate the manufacturing process with real particle shape? The answer is yes, right? And this is a paper that is now currently under submission, right? You can also address the calendaring process steps using machine learning. And this is something that we published also a couple of years ago. And here, basically what we have done is we play at experimental level with electrode formulation, with also we measure the thickness of the electrode before applying the calendar, before the calendaring process. We also play with the calendaring pressure. And then so we inject this experimental information into electrode microstructure generator based on a stochastic algorithm. So basically this is a generator of 3D microstructures of electrodes, right? Where you can so nicely locate in space active material particles, CVD, and pores. And then so we characterize these virtual microstructures in terms of a series of properties such as the tortuosity factor, the surface area of contact between active material and pore, which is supposed to be the active surface area, right? Because the pores are supposed here to be fully filled with the liquid electrolyte. And then we train with this data set, so a machine learning model that is able to perform regression predictions, right? And when I'm talking about regression, I'm talking about predicting numbers, right? And here you see a couple of examples of what you can get with this model. So you can predict the influence of the calendaring pressure and the electrode formulation, and also the porosity before calendaring on the tortuosity factor of the electrode, okay? Here, instead of having a phase diagram, that in the case of this coating and drying process that I was describing before, here you have curves, right? And then these curves, what I'm telling you is what is the value of tortuosity factor that you should expect if you apply a given pressure in your calendering process, if you have an electrode with a given porosity before the calendering, and if you choose a specific formulation, if your electrode have a specific formulation, that means a ratio between a weight percentage ratio between active material, carbon, and binding. The numbers that you see here corresponds to the porosity attained after the calendering process step, right? And here you see that there is a very strong sensitivity, right, of this tortuosity factor evolution with the calendering pressure, because of course, when you increase the pressure upon calendering, so the tortuosity factor increase. This is something that we have already studied before in one of my previous slides. But also what you see is that degree of increase of this tortuosity factor depends on the electrode formulation, but also depends on the porosity that you have before the calendering, right? So this once again shows the complex interdependency between parameters, because here I'm talking about calendering pressure, I'm talking about formulation and porosity of the electrode before calendering, and how these parameters will impact the tortuosity factor of your electrode. Machine learning is a wonderful tool to unravel these correlations, right? And establishing this correlation just by hand and analyzing, the data set that you have, for example, an Excel file by hand, it will be very challenging, right? You can go a step beyond. So with this machine learning tool applied to the calendering, so you can also include other parameters such as, for example, the roll speed in the calendering process or the roll temperature, okay, in this calendering machine. And you can investigate how these parameters, together with the roll gap, which is related to the pressure that you apply in the electrode upon calendering, how these parameters will impact, for example, the volumetric capacity of your electrode or electronic conductivity. And once again, so you can build these very nice maps, right? That are actually 3-dimensional or 4-dimensional, right? But here I'm just showing 2 dimensions. I'm showing the roll temperature and the applied pressure. So it's a heat map. Here you have in the other axis the volumetric capacity, right? And you see that in that way, so you can very quickly decide which parameters you need to adopt in the calendering machine in order to maximize the volumetric capacity or the electronic conductivity of your electrode. The next step, talking about then the digitalization of manufacturing process, is the electrolyte infiltration, right? Very important step because we want the pores inside the electrodes to be fully wet with liquid electrolyte. This is something that we can simulate using physics-based models, in particular using a technique called lattice-Boltzmann method, okay? What is lattice-Boltzmann method, or LBM model? So LBM model is a model which represents fluids as a collection of particles moving, okay, following some specific rules of motion. And this fluid which is being represented can be the liquid, in this case the electrolyte, but also it can be a gas like the air, which is initially present in the porosity of the electrodes, right? So here in this video, you see the ships, right? So this is not a simulation with LBM, so this is real life, right? But it's just to give you the feeling of how this model looks like. So basically, if you zoom a lot into the model, you will see particles moving. But when you zoom out, you will have the feeling that this is a continuum, right? And you will see a fluid, moving actually, yeah, but actually it's a collection of particles which are moving in the model, right? Well, this is what you see here. So this is, let's say, the macroscopic view of the result of the LBM. So imagine that there are a lot of plenty tiny particles moving there, but you have the feeling here that this is a continuum. And you see the result for the infiltration of electrolyte on an uncalendar electrode, which is very quickly, and the simulation of the infiltration of electrolyte in a calendar electrode, which is very slow. And the reason is that in a calendar electrode, you have higher tortuosity factor, right? Pores are interconnected with each other, right? But the more we are away, and then for the electrolyte, it's more difficult to go through, right? So this is something that the model can recover very well, right? This is good news, right? This is kind of trivial. But something that the model can provide as well is a prediction of where the air is going to remain trapped inside the electroporosity. And this is very important because this means that if you have air which remain trapped in some regions in the electrode volume, you will have then some part of the active material that is not going to be properly wet with the liquid electrolyte, right? And then so you are not exploiting the maximal capacity of your electrode, right? Because then you have some parts of the active material that we have more troubles to be intercalated with lithium ion, for example, or they're going to be deintercalated with lithium ion. This wettability phenomenon, so it strongly depends for sure on the electron mesostructure as we study, as we see today, right? So if you have a calendar or uncalendar electrode, so the speed of infiltration of electrolyte will be different. But also, so it depends on the contact angle of the electrolyte with the electrode. It depends also on the electrolyte density, and it depends also on the electrolyte viscosity. These are all the parameters that you need to take into account. You need to take into account in order to optimize the infiltration process of the electrodes by liquid electrolyte. This is something that we have extended so yesterday, okay? So we published this paper yesterday, which is an extension actually of this work, where we screen different wettability actually of different electrode microstructures, right? And here, so we are playing with the uniformity or heterogeneity, I would say more in that way, of porosity and particle size distribution of active material in anode and cathode. So this is a simulation of the infiltration process now in the full cell, right? In the sandwich, where you have on one side, so the anode, in the other side, the cathode, and you have the separator, right? Using here tomography images as microstructures for these simulations. So what we can do here is we can explore how fast this electron infiltration will go through these different configurations, right? Here you have electrodes with homogeneous porosity, right? So, and here you have electrodes where you have a gradient of porosity along their thicknesses, right? But also you can do the same with the particle size distribution. You can imagine, for example, in this side, you have particles which are smaller, and here particles which are larger, right? And the same for the cathode, right? And here you see an example for this second case, where you study the influence of this distribution of particle sizes along the electrode thickness. Basically, you have a bilayer structure, so you have smaller particles in one side and bigger on the other side. And then you compare that with a homogeneous particle size distribution in the full volume of electrode. I will play the video again. So you see that the heterogeneous case so offers a faster wettability, right? Infiltration of electrolyte looks to happen faster, right, compared to the homogeneous case. And this is exactly what is summarized here in this figure. So if you have an electrode with a bilayer structure, right, where you can tune the porosity, you can tune the particle size distribution. So you use maybe smaller particles in one layer and bigger in the other layer, or bigger pores in one layer and smaller in the other layer. You can speed up the saturation of your cell sandwich, okay? You can basically accelerate the electrolyte infiltration of your cell, right? We believe this work is interesting because it can pave the way towards a computational screening of the influence of electrode microstructures on the wettability of the lithium-ion battery cells. In order to do high throughput screening with computers, the optimal way will be using a machine learning model, a surrogate model, instead of using the LBM, because the LBM is computationally costly, right? So one of these simulations I showed you in the slide before, it can take a couple of days, right, to run. While a surrogate model can run in a few seconds, right? So here is what we have performed in this work that we published last year. So we have derived from the data coming from these LBM simulations of electrolyte infiltration, a machine learning model that is able to predict the saturation curves. That means the amount of liquid that you have per unit of volume of pore, in your electrode microstructure as function of time. So for different pressures, right, that are being applied upon this infiltration process. And this model is also able, this machine learning model is also able to reproduce very nicely the trajectory of the liquid electrolyte in the pore network inside the electrode, right? The advantage, once again, of this surrogate model based on machine learning is that it can make predictions in few seconds instead of a couple of days. That is what you need with LBM, right? And this is why, so we believe that this surrogate version now of this infiltration model can really pave the way towards high throughput screening to find the optimal conditions to infiltrate electrodes in a proper way. I mean, to maximize the wettability of electrodes with the liquid electrolyte. The last step towards the digitalization of this battery manufacturing process is, of course, the electrochemical performance of these virtually generated electrostructures, right, from the manufacturing simulations. Here you see the entire workflow. So we start from the simulation of slurries and also the calendering. So using CGMD, the drying, of course, as well. So using coarse grain molecular dynamics, and discrete element method. We can use lattice-Boltzmann method or the surrogate version of the LBM using machine learning to predict the electrolyte infiltration. And then the resulting microstructures, which consist on this spatial localization of active material, CVD, and electrolytes in the volume, can be meshed using our enough software to then inject the resulting mesh structure in a software able to simulate the electrochemical behavior of the electron, right? In such a way, so you can, for example, predict the lithiation or the lithiation dynamics of your electrodes so in 3D, right? By accounting for the physics going on in these electrodes, such as the transport of lithium ions in the electrolyte, the diffusion of lithium in the active material, the Walter-Bormann equations for sure describing intercalation, the intercalation, and the electronic transport in active material, and CBD, this, which means carbon binding domain, which is taken into account explicitly, okay, in all this modeling workflow. So we have published several papers, and here I'm showing just 3 examples, reporting results of how this electrochemical performance model can be used to gain insights on the impact of the manufacturing parameters on performance. And here you see the impact of formulation, for example, on an EMC electrode on impedance, on electronic impedance and ionic impedance. This is a simulated symmetric cell experiment. And you see that the impedance, both electronic and ionic, is highly heterogeneous, highly anisotropic, and the reason is that the CBD is located in a very heterogeneous anisotropic way inside each of the electrodes, right? Also, you see that this framework is also capable to study the impact of particle shape, in this case, graphite particle shape, on the lithiation dynamics of graphite electrodes, right? And here you see the case for spherical graphite and for more ellipsoidal shape for graphite particles, representing different type of graphite particles that we can find in the market to manufacture electrodes, anodes. And also here you see the impact of predicted impact with this model of the calendering degree on the lithiation, the degree of lithiation at the end of discharge of NMC electrons, right? You see that the model is capable to capture the influence then of manufacturing parameters on performance, but the beauty of this model is that it can capture this in 3D, in 3 dimensions, right? And also as function of time. And this is one of the latest works that we have published. So this was, I think, 1 month ago. And here, so we explore the influence of the CVD morphology on the discharge performance of NMC electrodes for high porosity electrodes, HP, and for low porosity electrodes. And here, so what we show is that the electrodes having so this aggregate CVD morphology, they'll perform better, okay, if you compare for high porosity, this the green curve with the red one, okay, versus film, they perform better versus the CVD morphology, and the same happens for the low porous electrodes, right? And we should highlight here that this CVD morphology can be controlled by the drying process, right? And you see once again the interdependency between manufacturing parameters and performance. And this modeling framework, which I'm presenting to you today, is capable to deal with that, with this link between manufacturing parameters and performance, all in 3D, right? Now let's talk a little bit of how we integrate all these models, right? That I show you, this constellation of models, physics-based machine learning, right? And how we, based on all this integration, we offer online services, you know, to researchers like you, but also to sometimes even to the general public, right? Or battery stakeholders in general. So first of all, this is a recap of this artistic project workflow. So we have in one side experiments going on in our prototyping line, so where we perform fabrication of slurries, coating, drying, calendaring, and so on and so forth. And then we have all these physics-based models which are sequentially linked. We simulate the mixing, which is something that I didn't talk today about because paper is still not written, right, on this. Then so the output of mixing goes into the slurry model. The slurry output goes into the coating drying model. So then the output of this model goes as an input of the calendaring model. The output of the calendaring go into the electrolyte model. And the output of the electrolyte model goes as an input of the performance model, right? We have this workflow sequentially coupling all these physics-based models, which are all 3D resolved, describing each step of the manufacturing process. Now, what we are doing, and this is something that we start to release already, and the paper is reported here, and you can get access to this service now for free, is we are integrating these models in a graphical user interface in the project webpage. And basically, so you can connect here for free. You will create actually, you will enter an email, you will receive a password, and then you will enter to this graphical user interface, which will allow you to perform simulations of slurries, of drying, and of calendaring, just by playing with experimental parameters, right? That means that you don't need to have any knowledge on computations, because I told you this is a graphical user interface, right? We want this to be user-friendly, actually, for everyone, including experimentalists. And here, so in this platform, so you can play, for example, with the particle size distribution of your active material. You can also play with the solid content of active material in your slurry. You can also play with the calendaring degree of compression. You can play with the drying rate, and so on and so forth, right? So thanks to this online platform, so basically you configure your design parameters for simulating your design manufacturing process. And then this will launch simulations in our computational cluster in our university. And then once the simulations are finished, you receive an email with the results, right? And then the concept here in this platform is that the results are shared with the entire community. So there is no private access to the results. Actually, once the results are obtained, they are stored in the database and they are findable by all the community which has logged into this platform, right? But also you will be pointed, thanks to the email, to your specific result, the result that you want to simulate, right? You want to obtain from your design simulations. And here you see some other details of how this interface looks like for the slurry step, right? Right now, we have something like more than 200 simulations performed. I mean, this screenshot is from January, right? And right now we have 300 users, 75% from academia, 25% more or less from industry, right? And here you see the kind of results that you can retrieve from this, because you can download the results for your own research. You can download these 3D microstructures and the information associated to these 3D microstructures, such as the porosity, the density of the slurry, and so on and so forth, for your own research, okay? Last but not least, I mean, regarding the integration, so what we are doing is combining in the artistic project these experiments with physics-based models, and this is what I talk about today. Also with machine learning, I also talk today about that. And basically the idea is that we are generating hybrid data sets containing experimental results of manufacturing parameters impact on electrode properties and performance, but also we are doing the same from modeling side, right? Because these models are validated in part to experiments, right? Then once these models are validated, they can be used to generate extra data points, right? And then you get a hybrid data set. And then this hybrid data set containing simultaneously experimental points and modeling points can be used in machine learning models, making predictions in terms of classification, for example, and the example of the influence of slurry properties on electroporosity is something in that scope, or regression predictions, right? And now what we are doing, also in collaboration with Elixabete, so we have a co-supervised PhD student, Marc Duquesnoy, who is funded by ALISTORE. We are actually demonstrating that this concept can be integrated in an optimization algorithm that can actually be used to maximize and minimize properties simultaneously, okay? And this is, I believe, is very useful and very interesting, because you can show that using this, for example, synthetic data sets, I mean, data sets produced from these physics-based models, you can perform optimization of the electrodes. I mean, you can come out with optimal manufacturing conditions, the manufacturing conditions that you need to adopt in order to make an electrode with, let's say, with maximal electronic conductivity, right? This is what I'm talking about here. I cannot disclose more because this is paper in preparation, but it will be submitted in a few days. And I believe that this concept is going beyond, let's say, autonomous battery manufacturing, okay, using robots that they can take decisions on the fly. They can optimize on the fly the battery manufacturing process just by collecting data from the on-the-fly characterizations, for example, of electrode thickness, but also from collecting data coming from physics-based models, right? I think this is the long-term vision that we have for this project, which I think it nicely fits also to the roadmap of Battery 2030 Plus that was presented by Eli. Let me conclude with some final words for the last 5 minutes. So about education and training. So, we are working very heavily on the use of virtual reality and mixed reality, I mean, since already some years. And we have developed in this context several serious games. which will allow you, for example, to navigate inside electron microstructures to calculate the tortuosity, right? The geometrical tortuosity of the electrons. This is a game which is very useful to make students understanding that the tortuosity is an anisotropic property, right? Also, we have a game where we invite students to drive electric car with different battery technologies, different type of active materials, and then in that way they can understand how these battery types, they influence the autonomy of the electric car. In this case, you need to collect 3 presents, which are randomly distributed in a virtual city in the shortest time as possible, right, by escaping from police cars. And also we have developed a game which simulates a smart grid where the car now can be recharged in recharge stations only if you have electricity available in the grid. And this electricity which is available in the grid is available in the grid because you produce it using 3D printed objects which represent windmills, and in low scale, and also solar panels and other devices, right? This is an interactive game, so it can be played up to 20 students. They can play together, and you have students that will generate electricity, will distribute electricity, and so on and so forth, interacting with these objects, okay? While the other student is going to drive the electric car, right? But if there is no electricity in the grid, so then for that student it's not possible, it will not be possible to recharge the car. So then this requires collaboration between the students producing electricity in the real world and the student driving the car in the virtual world. So these objects are interconnected with each other using Bluetooth technology, okay? And this is a concept that we published in Batteries and Supercaps in 2020. And for that, we have received one of the, for all this work, we have received one of these national prizes for pedagogy innovation in 2019. So recently I won a ERC proof of concept grant. So for a project called Smartistic, where we intend to embed the artistic models, the machine learning models and physics-based models in HoloLens technology. So this is actually a technology which allows to basically see holograms superposed to the real environment. And the idea with this is providing assistance for training and for research directly in the place of experimentation and directly in the place where we manufacture battery cells, right? And last but not least, this is something I promised in Twitter. So I was going to show today a new concept of digital twin. And this is actually a game that we have recently developed, which actually invite people to navigate inside our prototyping line, right? And allow people to interact with the parameters with the different machines, but in a gamified way, right? And then the idea here is fabricating cylindrical cells, right? And here you see the interaction with the mixer, right? Then you take the prepared slurry, you will perform the coating, right? You will perform the drying after you choose the right parameters. You will see then what happens. And then, so I believe that this is actually somehow resonating with this quotation from, which is attributed to Albert Einstein, plays the highest form of research, because this kind of tool can be very useful for sure for training, right? And for introducing people how we manufacturing cells in an interactive way, right? Because you can interact with this object. So through an internet browser, okay? I forgot to mention, this is very important. This game is going to be published through the artistic webpage and through our university webpage. And you can play with the mouse of your, of your computer, okay? And I believe also that this game can be also maybe a starting point for a new way of doing research, because we can imagine embed in this kind of graphical representation having machine learning models or physics-based models that make predictions of what is going to happen when you will play with the parameters of calendaring in some way and no other way, right? And maybe it's another way of making computations, right? Instead of learning about programming or using classical graphical user interfaces, you can basically perform simulations just by interacting with objects in the virtual world. So what we plan to do with this game is also putting it in a virtual reality environment. In that case, you will have full immersion, but in that situation, you will need a headset, right? This is my last slide. So I would like to invite everyone to this, the third edition of the Artistic Webinar Series, which is something that we organize every year since 2020. And we have a great panel here of invited speakers. Two of them, Isidora and Simon, that are heavily involved in Battery 2030 Plus, Big Map, and so on. But also we have other very nice speakers in this event. This is a free event, so you can register for free. The website allowing registration will open very soon. Please keep tuned through Twitter and LinkedIn, I mean, through social media. So we will communicate about that. You are very welcome to attend, and there, so you will be able to attend the talks from these invited people, but also from my PhDs and postdocs working in the artistic project, right? Who they are going to present the latest progresses and the latest results achieved in this project. Thank you very much to all, and thank you very much again, Kristina and Eli, for the kind invitation and this opportunity. And well, I will be very happy to answer questions if you have. Thank you.